So we're trying to answer this question for what values of x does this sequence converge. And so we're starting with the ratio test, and we're looking at a sub n plus 1 over a sub n, and then we're going to do the limit of the absolute value. So let's look at what that is. So hopefully you're getting used to how to do a sub n plus 1 over a sub n by just going, first put the a sub n as it is, but with n plus 1. So just put that in normally, but with n plus 1. And then flip it over, just flip that over, n over x minus 3 to the n. So we put the expression normally with n plus 1, then the reciprocal with just n. And that's how we handle a sub n plus 1 times a sub n over a sub n every time. And then we just simplify what that is. So we get starting to really typically see how these things fall out. We're going to have some part of it that's just going to be like n over n plus 1. Let's put that together. And then we're looking at things like things that have exponents, and one exponent is going to be one more than the other exponent. So everything's going to cancel out except that 1. So I'm just going to have x minus 3, and it's in the numerator. I could put it over 1, but I don't feel like it. So that's what a sub n plus 1 over a sub n is. And then I'll look at what is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. I need all this stuff to count as my justification. So that is equal to the limit as n approaches infinity, having done my scratch work up here, of the absolute value of n over n plus 1 times x minus 3. And then I can look for parts that we know are positive, so we pull them out of the absolute value. So n and n plus 1 are always positive. So I have limit as n approaches infinity. I'm going to pull the n over n plus 1 out of the absolute value. And also things that don't depend on n, like x minus 3, those can be pulled out of the limit. So it's going to be just times absolute value of x minus 3. So now the limit's only applying to the n over n plus 1. And the absolute value of x minus 3, we don't need a limit because there's no n in it. Then I can just observe that we have same degree, top and bottom, ratio of the coefficients. This limit is 1. So I have 1 times absolute value of x minus 3. So that's just absolute value x minus 3. So that's what my limit as n approaches infinity of a sub n plus 1 over a sub n is. It's absolute value of x minus 3. So now you want to remember that the series converges absolutely. The series converges, and therefore converges, for L, which is, this is L, less than 1. So this is what we call L right there, is that limit. All right, so that just means whatever we got here, we just set that less than 1. So we say absolute value x minus 3 is less than 1. So now I have to be able to solve this absolute value inequality. So hopefully you remember from calculus how to do that. So we're going to say negative 1 is less than x minus 3 is less than 1. Then we're going to add 3 to all three sides. 2 is less than x is less than 4. So we now know that the series definitely converges absolutely, and therefore converges for x between 2 and 4, but not including the endpoints. But here's the trick, is that when L equals 1, we get no conclusion. When L equals 1. We know if L is more than 1, then the series is going to diverge. But when L equals 1, we don't know. All right, so we have to test the endpoints separately. And that's going to be always part of this when we're looking for what values of x the series converges for. We have to test the endpoints separately. So really what we're creating here is an interval, right? This is an interval 2 to 4. And this interval has endpoints 2 and 4. We need to test them separately because either endpoint might converge or not. So how we're going to do that is we're just going to look and say, well, if x equals 2, what's the sum? The sum is the sum from n equals 1 to infinity of 2 minus 3 to the n over n, just substituting 2 for x. All right, well, I know what 2 minus 3 is. It's negative 1, so I have sum n equals 1 to infinity of negative 1 to the nth power over n. And now see, here's why I studied all those other different types of series, because I know what that is. That is the alternating harmonic series, and I know that the alternating harmonic series converges. And I might get something different from that. I might need something that I have to do a comparison test or something. Who knows? But I got something a little clearer here. Now, what if x equals 4? That's my other endpoint, so I'm testing my two endpoints. Then I would have the sum from n equals 1 to infinity of 4 minus 3 to the nth power over n. Well, that is the sum from n equals 1 to infinity of 1 to the n over n. Yeah, all right, so it's just 1 over n. So that's also sum from n equals 1 to infinity of 1 over n, and that is the harmonic series. And we know that the harmonic series diverges. All right, so now we know for what values of x the series converges. So the series converges on this interval from 2 to 4, including the 2, but not including the 4. So it converges on the half-open interval from 2 to 4. So series are always going to do this. Power series are always going to do this. It's an important idea. They're going to converge within an interval that might be closed on both ends or closed on only one end, but it'll converge inside the interval and diverge outside the interval. So we're going to think of that, interval from 2 to 4 as being centered on the number 3, which is in between them. So if I go out 1 either direction, what we call that is the radius of convergence. So we say that the interval of convergence is 2, 4, and the radius of convergence is 1. And we will talk more about these as we go along.